And it's really pleasing. It's really a pleasure for me to introduce Professor Kumar to all of you. And the senior people, like in India, most of the researchers, I don't need to introduce Kumar. Everyone knows, because Kumar and his brother Ram Murty, both of them are, so good with the Indian students. So many of them, I'm one of the beneficiary that we go there and they train us, and then we come back here. So this is a real privilege for us to have Kumar Murty with us. He is a professor at University of Toronto and also the director of the Fields Institute of Research in Mathematical Sciences. So he has got, if I start listing them, the awards and other things, so it will be a long list. But I can tell you he is a fellow of the Royal Society of Canada. He's a fellow of Indian National Science Academy. And then he has got awards like Coextra Gems Award from Canadian Math Society and many other things. And his area of research is very interesting to all of us. It's a most fascinating area that he works in analytic number theory, algebraic number theory, arithmetic algebraic geometry, and information security. In fact, he is the founder of Ganita Lab and is co-founder of Perfect Cloud. And there is another, Pratha Technology. So he has other interests also. So we are really privileged to have Kumar you here. So Professor Kumar Murty.
Thanks very much, Kalyan, for the very kind introduction, and delighted to be speaking with you, albeit over this electronic medium. Kalyan was just remarking about my background, and I was just saying that given the current situation with the pandemic, maybe this might be the safest place to be speaking from. So I want to chat with you about the Find Selmer group, and I'm going to motivate it. I want this to be as accessible as possible. Some parts of it will be, will give a lot of background. At certain parts in the talk, maybe I'll go a little fast about some technical things, but the idea that I want you to take away from this is a really, really ripe subject for a lot of interesting problems and a lot of interesting investigations. It's something that in some sense could have been done a long time ago, but it only seems to be becoming active now. And so I will try to explain what it is and what's going on there. So let me start with some background. We have a number field K. Number field means it's a finite extension of the rational numbers. And something that algebraic number theory is really keenly interested in is a finite group called the ideal class group of K. So it's a certain finite abelian group. And what it does is it measures the deviation from unique factorization in the ring of integers. The ring of integers means the integral closure of Z inside K. So elements of K that are integral over Q. So for example, if you took the rational numbers, the class group is trivial because we already know that the usual integers have unique factorization. But if you just change Q just ever so slightly, for example, by joining square root of -5, suddenly the class group becomes non-trivial. It's Z mod 2, in fact. And that sort of reflects the fact that you have this kind of phenomenon here, that you have irreducible elements 2 and 3 and 1 plus minus root minus 5, and 6 can be factored in two different ways. So that obstruction is measured. That's the kind of obstruction that the class group tries to measure. And in the case of this simple quadratic field, it is Z mod 2. Now, the origin for studying this is actually not because it's a neat thing to wonder about unique factorization, but unique factorization is a tool that's used a lot in Diophantine equations. So in particular, if we try to solve Fermat's last theorem, Kumar observed a long time ago, and maybe, yeah, I think Kumar observed a long time ago that if you had unique factorization in the field Q, where you adjoin a pth root of unity, this Q of zeta p, then you could prove the Fermat equation has no solutions. And then more generally, Kumar showed that as long as you don't even need this group to be trivial, as long as P doesn't divide the class group of Q zeta P, that argument still works. Because this has no non-trivial solutions. Unfortunately, the problem is that this condition is not always satisfied. P indeed can divide the class number of Q zeta P, and it could be quite large powers too. But anyway, the class group is mysterious. So it is such a fundamental object, and still it's mysterious. On the one hand, and this is true even, as I say, if you look at the simplest cases of number fields, quadratic fields, one may argue whether the quadratic fields are in fact the most simple or the most complicated of number fields. But anyway, Gauss conjectured that Gauss conjectured, how do I go back? Gauss conjectured that if I look at a real quadratic field, in other words, Q adjoint square root of D, where D is positive, that for infinitely many such D's, the class number is trivial. In other words, that you do have unique factorization there. And it's still an open conjecture, as you know. On the other hand, if I look at imaginary quadratic fields, Q adjoint square root of minus D, where D is positive, if this class number is small for infinitely many square free D, we are in serious trouble because it contradicts the Riemann hypothesis. So these two fields, though they look superficially the same, this is adjoining square root of a positive number and this is adjoining square root of a negative number, the class group behaves radically differently. Here you could have a very small class group infinitely often. And here, if this were to happen like that, then you have violation of the Riemann hypothesis. Okay, so see if I can go to the next slide. Yes. Yeah. So when something is hard to study like that by itself, then you think about, what about if I vary the field? What about studying this in a family? So that's a natural thing to do. Can I study the class number as I vary, not in a fixed number field, but as I vary in a family of number fields? And the answer will really depend on what we mean by a family. So I'll tell you two simple kinds of families. One I call a horizontal family, and then later we'll look at what you might call a vertical family. So horizontal family, let's say we vary over quadratic fields. So it's horizontal in the sense that I fix the degree, it's 2. Okay, I'm varying over quadratic. Let's be even more precise. Let's say we were varying over imaginary quadratic fields, since we got already sensitized to the fact that class numbers may behave differently in real and imaginary quadratic fields. Let's look at imaginary quadratic fields, Q root minus D with D positive. So let's set so I don't need to write this out, HD to be the class, the class number, in other words, the order of the class group. In some sense, here we expect that the class number is somehow close to square root of D. And I've just wrote this squiggle here. I don't mean that HD is asymptotic to root D in the sense that the quotient goes to 1. That's not true. But somehow it should hover around square root of D. That's, in other words, class number should be large relative to the discriminant. So to see why one would make such a assertion, the connection comes through L function. So for this quadratic field, Q root minus D, we have a certain character, quadratic character, given by the Jacobi symbol, if you like, chi D. And using that, we can create an infinite series, summation n equals 1 to infinity, chi d of n over n to the s. Let's call that LS chi d. So if you're seeing this for the first time, it might strike you as kind of strange that you have this arithmetic problem, and to address it, you're constructing this analytic object. And now here S is a complex number. But the mystery of these things, of these L functions, is two things. Firstly, they're much more pliable, especially when you move in families rather than the fields themselves. And second thing is, these L functions seem to know a lot about the field they came from, even though we didn't put it into the definition. So in particular, there's this beautiful formula of Dirichlet that if I evaluate this series at S equals 1, the class number shows up. It's with the value at 1 is essentially class number divided by square root of D times some simple factor. So the most important thing to note is the class number suddenly shows up in the L value at 1. Okay. Now, as I said, the L value is useful to have because I can study L functions in families. So if I vary over the Ds and see how big is this L1 chi D, well, I can just substitute the Dirichlet series. It doesn't converge absolutely, but it does converge conditionally. So it's chi D of n over n. And then you just argue that, look, you can argue this in several ways, but you might say that averaging over chi's characters should be small when the character is non-trivial, because characters in general have built-in cancellations. So you will say that the dominant piece of this is when the character is trivial. Now, this is a quadratic character, so it's going to be trivial whenever the argument is a square. So the dominant term, that's what I mean by the squiggle here, is going to be the same sum over D, but now I only go over squares. So in that case, this is 1, and I have sum of 1 over m squared, which is zeta of 2. So I get a constant times x. Especially if I'm going over fundamental discriminants, the constant is not just zeta of 2, but something else. But anyway, you get you get roughly, it's growing like constant times x, which means that I'm averaging roughly constant times x discriminants. So on average, this is behaving like a constant. So now if you go back to Dirichlet's formula that L1 chi d is class number over square root of t up to some minor factor, and L1 chi d is staying bounded or is constant on average, then that means class number on average is going to behave like maybe up to constant square root of t. Okay, that's the idea of this kind of expectation. Now you might ask, in doing this, where did we use the fact that chi d corresponds to an imaginary quadratic field? I just said you have a quadratic character. We didn't really use the fact that it's whether it's an even character or an odd character. Where did we use the fact that chi d corresponds to an imaginary quadratic field rather than a real quadratic one? We didn't. Well, that might bother you, because didn't we just say that class numbers behave differently in imaginary quadratic versus real quadratic fields? Yes, they do, but the L function in this average sense doesn't. And so what it means is that L1 chi d is still constant even if I go over real quadratic fields. But the point is the Dirichlet formula changes. L1 chi d is no longer just class number over root t. There's an extra term, a very mysterious term, which is log of the fundamental unit. So it's a certain unit in the field of smallest, which is a generator of the unit group, of the infinite part of the unit group. So the calculation means if this is constant, that means class number times log of the fundamental unit is still growing like square root of t. Okay. So this is the defect that you get, that you cannot separate the class number from this, what eventually will become the regulator. Now the problem also is that this part can behave quite erratically. There's an old example of Chawla, I believe it's Chawla. Suppose you take an integer t, positive integer, not 2, and you look at t squared plus 1, and suppose this number is square free. So that happens lots of times. So call that d. And now let's look at q root d. Then you can show that the epsilon d, the fundamental unit, is t plus square root t squared plus 1. So you have an explicit expression for the fundamental unit in the field q root t. So then you notice this is behaving like square root of t squared roughly. So it's behaving like t. So this whole thing is like order of t, and t is like square root of d. So that means epsilon d is behaving like square root of d. So log epsilon d is like log root t. So it's about up to constant, it's log d. So if I go back to this formula, it tells you that hd is up to constant square root of d over log d. So the class number is large for those examples of Chawla. In general, you can try to make examples where epsilon d is even bigger. Here, epsilon d, as we said, is coming to be like log d. There are examples of Yamamoto where log epsilon d is like log d cubed. Okay, so here log epsilon d was like log epsilon d was like log d for this Chawla example, and he's got examples where it's like log d cubed, so much bigger for infinitely many d. But well, that will still not help you too much in terms of making class numbers small. It'll just replace this log d with log d cubed. You still got hd hovering near root t. So you don't get to Gauss's conjecture. But Gauss's conjecture, this is 1 infinitely often, which means this log epsilon d can be as big as root t. It means it could be huge. Okay. Now these results can be generalized by looking for fields of larger degree. So instead of quadratic fields, I can look for higher degree fields. In this case, I replaced the L function, the simple L function we were using, with the Dedekind zeta function. So it's defined as a sum over ideals, integral ideals of the field, 1 over norm a to the s. So the norm of a means it's a Dedekind domain. So every ideal is a finite index in OK. So the norm is simply the index. And this converges absolutely for real part of s bigger than 1. There's a simple pole at s equals 1, just as in the case k equals q. By the way, I hope it's obvious. When k equals q, zeta sub q is zeta, the Riemann zeta function. And Dirichlet's formula is replaced by something called the analytic class number formula. So what it is, absolutely one of the most stunning formulas in number theory. The residue at s equals 1, this has a simple pole at s equals 1. The residue is this beautiful formula. Why it's so beautiful, I keep saying it's beautiful, is because it packages so many invariants of the field into one formula. 2 to the R1. R1 is the number of real embeddings of the field. 2 pi to the R2. R2 is the number of complex embeddings of the field. Here's the order of the class group. Now here's the regulator, which is a bigger, higher order thing like the log epsilon that we saw in the case of the real quadratic field. Here is the number of roots of unity, okay, and then square root of the absolute value of the discriminant. So this is the analytic class number formula. On the other hand, the zeta k is not a simple L function. It factors into a product of other L functions. So these can be written in terms of Artin L functions evaluated at 1, where now chi's are not given by characters of the base field, they're characters of the they're Galois characters, and they may occur with certain multiplicities because I'm not assuming that k over q is Galois. The analytic theory doesn't seem to care about that. This formula is valid for any k, but because k over q is not Galois, you get certain multiplicities here. Okay, this is the analytic class number formula. Now the problem with using this is on both sides you have a difficulty. One is you don't have a single L function. Now you have a product of a bunch of L functions. And here you have the old problem, the class number is not alone. It seems to be together with this regulator, and we already had a difficult enough time in the quadratic case. We're going to have even harder time in the general case. So on the one hand, this is good, but on the other hand, it's a little discouraging. So we need to solve two problems. So one case in which you can use this very nicely is if I have a CM field K. So K is a CM field, which means it's a totally complex quadratic extension of a totally real field. So for example, Q adjoint zeta P is a CM field. And it has a unique maximal real subfield. I should have said maximal, it's maximal real subfield. So in the case of Q zeta P, it's Q zeta P plus zeta P inverse. Okay, so you fix some element of order 2, call that the complex conjugation, which is central, and you look at the subfield fixed by it. That's the maximal real subfield. Now, in this case, what you do is you don't apply the analytic class number formula to a single zeta field, but you apply to it and its real subfield, and you take the quotient. Then what happens? A nice thing happens. This RK by itself is a mystery, but when I compare RK to RK plus, the quotient is something simple that I can figure out. So therefore, the regulator issue disappears, and you get a piece of the class number, so-called minus part of the class number remains. Moreover, the L functions all collapse, and you get only one L function, namely the L function evaluated as 1 of the quadratic character that picks out K as a quadratic extension of K plus. Okay, now I can use this to study the problem in the case of vertical family. So for a fixed K, instead of looking at all quadratic fields, what I'll do is I will look at a tower. Okay, so I'm going to, instead of, now the degrees are increasing. Now I might look at a tower and we ask whether it's any more tractable. So it's again, the problem is related, if I ask the question of is the class number going to grow, the problem is related to zeros of L functions near s equals 1. Just like I told you that in the case of an imaginary quadratic field, if class number not growing means the Riemann hypothesis is false. So similarly, it happens here as well. But then under some hypothesis on the tower that you pick, you can essentially eliminate or mitigate that possibility. In other words, the effect, even if Riemann hypothesis were false, its effect on the class number is small. So one example where we could do this is if the extensions we're looking at all have solvable normal closure. I'm not assuming this by these extensions are Galois. I'm not assuming these K sub n's are Galois over the base or over Q. But if they have Galois, their normal closure, their Galois closure is solvable, then you can prove that the minus part of the class number grows at least as fast as the quarter root of the discriminant. There are some constants involved here. It's all completely effective and absolute. I did this some years ago. It appears in Compositio. And what's the method of doing this is a combination of both the group theory and the analytic number theory. Neither by themselves is sufficient. But what happens is when you put them together, it enables you to say that if the Riemann hypothesis were false and there is a 0 near s equals 1, it can't be too close. It pushes the zeros away from s equals 1. So you can find a good zero region near s equals 1. And once you have that, the danger to the class number is passed, and you can get a lower bound. Of course, you've lost something here. It's not a half, it's a quarter. But that's an artifact of this method, that you're not proving there is no 0 near s equals 1. You're just pushing it away a little further than it might be at first sight. Okay.
I have a quick question on that slide.
Yeah.
So what do you expect the behavior of the minus part to be square root?
Yeah, I think so.
Okay.
Yeah, yeah.
Thanks.
Right.
Yeah.
Right. In proving this, I wasn't trying to optimize it. So this came as an afterthought. So one might actually go back to the paper and see, can you squeeze a better exponent out of that method? I just haven't tried. It's possible. Okay. So on the other hand, in this vertical family, this towers, there's another approach that was initiated by Iwasawa. It's a more algebraic approach. It doesn't use the complex L functions. And it goes like this. So let's look at the special case. So I take a prime P, not just any tower, but I take the tower of P power roots of unity. So here's Q, then I join a Pth root of unity, a P squared root of unity, and so on. Okay, so now Iwasawa asks himself the question, not about the Archimedean growth of the class number, but the p-adic growth. So he asks about the power of P that divides the order of the class group at each stage. Okay, that was the question Iwasawa asked himself a long time ago in the 60s, I guess, was in his first paper. So late 50s, early 60s when his papers appeared. And what he showed is the kind of really beautiful and very striking theorem. There are constants, positive, non-negative constants, mu, lambda, and nu, such that the power of P that divides the class number of Q zeta P to the n has this structure. There's something times P to the n, there's something times n plus a constant. So in other words, P to this power divides this class number. Now you can imagine if mu is not 0, mu is at least 1, that means P to the n might be dividing this class number. Okay, it's possible. And the way he gets to this is by classifying certain Galois modules that are made out of class groups. And I'll explain to you what that is in a second. Okay. So more generally, Iwasawa will studies in more general towers than just the cyclotomic tower. But the cyclotomic tower, as you'll see, has a special place, even in classical Iwasawa theory and modern Iwasawa theory of elliptic curves. The cyclotomic tower seems to be special. It's not the same as any old ZP tower. So we'll keep coming back to that. And modern Iwasawa theory is more abstract than this. It looks at geometric variations of this, and even motivic variations of this. This talk, I want to look at the Iwasawa theory for elliptic curves. And when we do that, whatever that means, we'll see in a moment what that means. We'll replace the class groups with Selmer groups. And moreover, in this talk, I want to talk about a particularly special subgroup of the Selmer group called the fine Selmer group. This was known for some time, but is made famous, I think, at least for me, in a paper of Coates and Sujata. And what is special about this fine Selmer group? It seems to imitate the class group. So here is you try to do the Iwasawa theory for elliptic curves and Selmer groups, and you find a lot of things go wrong. It's not like the classical cyclotomic theory or the classical Iwasawa theory. A lot of things simply are not known, but then other things are simply false. And yet there seems to be a subgroup in here called the fine Selmer group, which starts to imitate the class group. And therefore there's some hope there that we can bridge these two theories. And there's a really striking conjecture I will show you of Coates and Sujata that will show that it's not just about making this theory more and more general, but actually it has an implication back to the classical case. There are lots of open problems here. If you're a student beginning in the field and want to look at an active area, I will tell you there are a lot of open problems here, and I think there are a lot of accessible open problems too. Now, because of the time, I'm not going to explain elliptic curves. I'm going to assume you either know it or you know where to read about it, or there are lots of good books now about elliptic curves. I'm also going to use Galois cohomology. That's the tool mostly in studying these things. I'm not going to explain Galois cohomology other than to say enough about it that you can follow it. But if you want to read about it, again, there are good expositions. In particular, I gave some lectures in Harish Chandra Institute last October. I think those notes or videos or something may be available somewhere. So catch hold of some HRI person and you might get hold of that. Okay, so what is the Selmer group? I have a number field K and an elliptic curve E over K. If I look at the points on the elliptic curve of an algebraic closure, that's a divisible group. Okay, divisible means that if I have any group element, any element here and an integer, then I can find, let's say I have a group element, let's say I have a point here Q and an integer n, I can find a point in here, call it P, such that n times P is Q. Okay, therefore I can divide a point by any integer. So what the implication of that is, if I look at the multiplication by n map on E of k bar, it's surjective. And the kernel is called E bracket n. So the points on E of k bar which are killed by n. So this is an exact sequence first of a billion groups, but in fact it's more than a billion groups because there's an action of the Galois group on all of these things. E is defined over k, the group law is defined over k. So all of these are actually modules for GK. So then I can take the cohomology long exact sequence when I have a module, when a short exact sequence of Galois modules. I can take the long exact sequence in cohomology and I get the following short exact sequence from that long exact sequence, namely E of k, k is now the ground field, modulo n E of k maps to H1 GK with coefficients in E bracket n, and this maps to H1 GK with coefficients in E killed by n. Oops, have to go back. Yeah, this if you haven't seen this sequence before, please stare at it and be very careful about it. There's a very subtle thing going on here that here I'm looking at cocycles valued in E bracket n. Here I'm looking at cocycles valued in E, but which are killed by n. Okay, there's an important difference between the two, and of course the fact is, it's important because the difference is rational points. So this very important group is sitting as the obstruction, the difference between these two. Okay, now the point of doing this is the group I want to study. Cohomology in general tends to be easier to study than rational points. But the question really becomes now, if I give you an element of here, how am I able to tell that it came from here? Because this image is certainly not onto, because the image of this is the kernel of this map, so it's not onto. This map has a kernel. So how do I detect from here that it came from rational points? So the way you try to do it is you try to throw at it all the possible conditions you can. Just as when, for example, when you try to show that a Diophantine equation doesn't have a solution, you try to see, does it have a solution mod P? And if you can show mod P doesn't have a solution, then it couldn't have had a solution to start with. So like that, so you look at local obstructions, you do the same sequence locally, you replace k by kv. Kv is the completion of k at v, where v is a prime of k. And you replace the Galois group with the decomposition group. GV is the Galois group, kv bar over kv. Okay, so again, the problem now is I want to use this to recognize elements of here which come from rational points. Okay, so then here's the top sequence is what we had before. The bottom sequence where I replaced k by the local sequence. And then do some little bit of diagram chasing, and you see that if I define now the Selmer group, n Selmer group, as the elements in here which go to 0 under this map. Okay, when I go from here to here, it goes to 0. So the kernel of that map. And the Shafarevich-Tate group is the things which go to 0 when I go down here for all these. Then the previous sequence, which looked like this, I replace H1 with the Selmer group and this one with the Shafarevich-Tate group. So you get a sequence that looks like this. E of k mod n E of k maps to the n torsion in Selmer, maps to the n torsion in Shafarevich-Tate. Okay, so now the idea is, if we've improved the situation, can we compute this? Can we figure out what this is? Okay. Moreover, you notice, by the way, the kernel here seems to be over all primes, but actually to check membership in Selmer, it's enough to check local triviality at a finite set of primes. In particular, if I take the primes at infinity and the primes of bad reduction, that's a finite set of primes, and local triviality at those primes is sufficient to be in Selmer group. Okay, so this looks like infinitely many primes, but it's only a condition at finitely many primes. And I'm using here the notation GS. GS means the Galois group not of k bar over k, but ks over k, where ks is the maximal extension of k unramified outside S. Okay. Now, in particular, if I take an odd prime p, you see here I just had this n, taking things killed by n. But for now, I can make those n's go over powers of a fixed prime. So to take an odd prime p and look at cell p to the k e, okay? And these things can be packaged together as I vary over the K, and I get the P primary part of the Selmer group of E over K. And the P primary part also satisfies this kind of exact sequence. Okay, now instead of E of P to the K, I have E of P to the infinity, which means any points on E rational over K bar which are killed by some power of P. Okay, so now the P primary fine Selmer group is just subtly different from this. Namely, I told you this, putting this bracket P infinity outside is an important point. What if we move it inside? The P primary fine Selmer group is the kernel of that map. So I actually keep the local conditions simpler, and I broom the bracket P infinity inside. That's the fine Selmer group. Okay. Now, obviously, we have a map always from H1 GV E bracket P infinity inside to the bracket P infinity outside. By the way, a simple way to think of when you think of an element of HV, after all, it is a map from GV to whatever module is here, only it satisfies some conditions. So you can imagine if the map takes values in E bracket P infinity, then it also takes values in E. The fact that it's killed by P infinity also has to be observed. In general, this is not an injection, but it is when I restrict to the fine Selmer group. So you get the fine Selmer group actually injects into the Selmer group. So it is a subgroup. Okay. Now there's an exact sequence. This subgroup, the quotient can be written in terms of local points on the elliptic curve at primes dividing P. But most importantly, notice here that at P infinity, the S has disappeared. Remember, I chose a set of places. This S was appearing, GS. Somehow the dependence on S disappears when I go to the limit. Okay. Now I want to do, so just as I'm not looking at just P to the K torsion, but P to the infinity torsion. Next thing I want to do is I want to replace K by an infinite extension of K. Okay, now I'm going to study these groups not over K, but over infinite extensions of K. Okay, this is where now Iwasawa theory of elliptic curves will really start. So F is a number field. I take an odd prime. Again, I'm looking at the cyclotomic, the tower. This is not the cyclotomic tower. It's the tower that I get by joining P power roots of unity. And let's call F infinity the union of that, the direct limit of these fields. The Galois group of F infinity over F is generically, it is ZP cross, if P is sufficiently large. And ZP cross is Z mod P star, it's a finite group of P through or P element of order P in here, times 1 plus P ZP, which by the logarithmic map is isomorphic to ZP. So what I want to do is I want to kill this finite group. So I find an intermediate extension between F and F infinity called F cyclotomic, such that this Galois group is exactly ZP. In other words, it's just this piece here. I want to kill this piece. Okay. So Iwasawa theory now, it looks at this group, this field right here, F cyclotomic, and it considers the maximal unramified abelian P extension of F cyclotomic. So those of you who've studied class field theory know that we're really, really interested in unramified abelian extensions. That's what classical class field theory studies, and we want the maximal ones. But usually we study that over number fields. This is not a number field anymore, it's an infinite extension of Q. And Iwasawa theory wants, nevertheless, to study the maximal unramified abelian P extension of F cyclotomic. P extension means that the Galois group is a profinite P group. We'll put an extra condition that every prime over P splits completely. Okay, let's call that thing K cyclotomic. And then Galois K cyclotomic over F cyclotomic. Then, so here is F. I took the ZP extension of the cyclotomic tower. Then I took the maximal abelian unramified P extension here, in which every prime over P splits completely. This Galois group is the thing that we're very interested in. It turns out to be a module. This was a ZP extension, but when I go to these completions, it becomes a module over a ring lambda, which is a formal power series in one variable over ZP. How this ZP, this lambda is connected to the limits of these ZP, that's a simple calculation, but let's leave that for now. It's a module over this ring. Now this ring is interesting. I hope I'll explain that. Let's see. Yeah, okay. So let's look at the picture. Here's F. At finite layers, I have Z mod P to the N extension, and here is the ZP extension. And at each finite layer, I can look by class field theory at the maximal abelian unramified P extension of Fn. So I get an XN module, sorry, a field Kn over Fn whose Galois group is Xn. There it is. And now Xn is the p-Silo subgroup. You can think of Xn as the p-Silo subgroup of the class group of Fn. And if I now take the union of these K sub n's, I get K infinity, and I call X the Galois group of K infinity over F cyclotomic. And this is a module over this Galois group here, which is Zp, but it's more than that. It's a lambda module because of this profile, these limits. Okay, so I'm not going to explain this. So it's you get it as a module over lambda. Now the point is lambda is not a PID. For example, the ideal generated by P and T is not principal. But nevertheless, you know, module theory over a principal ideal domain has a particularly nice structure. So lambda is not a PID, but nevertheless, it has a nice module theory. So here is 3 things to keep in mind. Sometimes it's confusing. If I have a finitely generated lambda module, the structure theory is it's got a free part plus a torsion part. And the torsion part is of 2 kinds. Either you mod out by a power of P or you mod out by a distinguished polynomial. And this twiddle here means pseudo-isomorphic. You've got finite and cofinite, finite kernel and co-kernels. Because that's what it means for X to be a finitely generated lambda module. Every finitely generated lambda module has this structure. You say such a thing is torsion if there's no lambda component. Okay, R equals 0. So then there's just these parts. Now the third thing is you say that X is fine. It is in fact, it is finitely generated as a ZP module if this part is also absent. So you just have this. Okay, this, I mean, I'm not saying anything. This is not rocket science. I'm just saying this is the structure theory for finitely generated lambda modules. Obviously, it's torsion if R is 0, and it's obviously finitely generated. To be finitely generated as a ZP module rather than as a lambda module means this part has to vanish. Okay, so if I set mu to be the sum of these mu i's, for this to vanish means mu is 0. Okay, so to say mu is 0 means that X is finitely generated as a ZP module. So Iwasawa proved that for the lambda module that you get from class groups, in the cyclotomic case, you get a finitely generated lambda module, and he conjectured that mu equals 0. So you get a finitely generated lambda module, means it has this structure. It's in fact is torsion, and you conjectured that mu equals 0. So there's a finitely generated ZP module. This is not known yet. It's known in some cases, for example, if F over Q is a billion, but in general, we don't know that the mu equals 0 conjecture. Okay. So even the classical cases, there are still big open problems in Iwasawa theory. By the way, you see, I added this slide as an afterthought. That's why the funny numbering. Okay, now for elliptic curves, I want to do the same thing, replacing the class groups with the Selmer group. So cell P infinity E over Kn. So I have a tower of extensions, and over each Kn, I'm doing this construction that I did before, cell P infinity E over Kn. And then let's assume that the Galois group of the whole tower is Zp. Nowadays, people consider more general things, a periodic Lie group, for example, GL2Zp. And we may consider now cell P infinity not just over E over Kn, but over K infinity. This is the main object of study when people talk about the Iwasawa theory of elliptic curves. And here's a fact. It's finitely generated module over lambda. It is, okay, it's a finitely generated module over lambda, therefore the classification theory applies to it. Is it a torsion lambda module? Yes, for if this tower is not any old tower, but the cyclotomic tower. Okay, so for the cyclotomic Zp extension of K, we expect that the Selmer group is torsion. Okay, then you can ask, it's torsion, but is mu equals 0? And that is false. The Selmer group can have non-zero mu. That's an old example of Maser. But here's the following striking conjecture that Coates and Sujata make. They call it Conjecture A. It's a really very interesting conjecture. That if I take the cyclotomic tower, then the Pontryagin dual of the fine Selmer group is finitely generated as a Zp module. In other words, it's torsion as a lambda module and mu equals 0. So in this elliptic curve context, where for many years people quoted this as saying the mu equals 0 conjecture doesn't hold in this context. There is a distinguished subgroup for which it does hold. It is conjectured to hold. So in some sense, this is one of the ways in which I say the fine Selmer group seems to imitate the class group. And it may make it more amenable to study. The goal of the work that I'm doing now with my former student and now postdoc, Devanjana Kundu, is to look at this whole thing and to understand how it interrelates from fine Selmer to Selmer. So let's go back to fine Selmer at a finite level. So not at the infinite level, but at the finite level. So the finite set of primes containing S infinity. Remember, this is the definition. It's the kernel of H1 GS E bracket PK, P to the K, and which is locally trivial at the primes in S. And when I write it like this, I notice I introduced an S into the notation. That's because this group does depend on S. And to see that, here's the simple calculation. Actually, this calculation is instructive in any case. Let's suppose my field, my ground field K, is such that I have the P to the K torsion. Okay, so let's say E bracket P to the K is rational over K. Then what is this H1 GS E bracket P to the K? Well, remember, this thing is a Galois group of some extension of K over K. So since all these points are rational over K, this action is trivial. Now, in a simple fact about definition of homology, that when you have trivial action, the H1 is just homs, just ordinary homomorphisms from GS to E bracket P to the K. Well, this is an abelian group, so any such homomorphism factors through the abelian quotient. Okay? Moreover, we said this, so that's just this part. What about this? We've imposed some local triviality condition. Well, locally, also it's a hom. And we're saying it maps to 0. In other words, I have a homomorphism from the Galois group to this thing. When I restrict it to a decomposition group, it's 0. What does that mean? It means V splits completely in the fixed field of the kernel. And it's unramified. So that means that this whole thing is, GS means it's already unramified outside of S, and this condition, the Selmer condition, fine Selmer condition, is it's unramified at S as well. So in fact, it is completely unramified. So it's actually a hom from the S class group, ideal class group, E bracket P to the K. Okay, so in the case that you have this condition that the P to the K torsion is rational over K, the fine Selmer group is just homs from the S ideal class group to E bracket P to the K. Now, as an abelian group, E bracket P to the K is just 2 copies of Z mod P to the K. And therefore, if I write this thing here, this is just Z mod P to the K plus Z mod P to the K. So R P to the K ES is exactly this. The P to the K torsion, 2 copies of the P to the K torsion in the S ideal class group. Okay, so this already shows you how the fine Selmer group tends to imitate the class group. We have a more maybe a less obvious way in which it imitates. This is a result with Meng-Fai Lim that I proved some years ago, which involves P rank. So P rank of an abelian group means this, that it's the dimension of the elements killed by P over Z mod P. So for example, suppose M is Z mod P to the K, then the P rank is 1. Suppose M is a number of copies of Z mod P, K copies, then the P rank is K. So it picks out somehow how horizontal the thing is. Okay. So here's what we proved with Meng-Fai Lim, and this appeared in the journal Ramanujan Math Society a couple of years ago. So I have an elliptic curve, and I take a ZP extension whose primes above P are, and those of bad reduction split finitely. This finite splitting condition occurs often in Divisible theory. Suppose just the P elements of order P are rational over F. Then the P rank of the fine Selmer group and the P rank of the class group, or twice the P rank of the class group, differ by a bounded amount. Okay. Our method, the way we did this also shows that we can reprove, excuse me, a theorem of Coates and Sujata, that if I look at the cyclotomic ZP extension and some conditions here, conjecture A for E over F infinity holds if and only if the mu equals 0 conjecture holds for F infinity. In other words, the classical Iwasawa conjecture for F infinity is true if and only if conjecture A holds for E for this elliptic curve of infinity. Now that should strike you as something very interesting. Why? This statement doesn't involve elliptic curves. Iwasawa's conjecture about mu equals 0 is just about the ZP tower, the cyclotomic tower, in fact. And this is a statement about elliptic curves. So that means that if you can prove conjecture A for one elliptic curve, you deduce mu equals 0. Well, that's
Can
really
you
interesting.
can you remind us what is conjecture A just again?
Yeah, conjecture A is this mu equals 0 for the dual of the fine Selmer group. So that this is a torsion lambda module and mu equals 0 for this. So in other words, when I write it as a number of lambda modulo certain ideals, you don't have any powers of P. So if you can prove mu equals 0 for one in the fine Selmer for one elliptic curve, you get it. You get the classical mu equals 0 conjecture. So that begs the question whether now we can actually do something if we were to vary the elliptic curve. We don't know yet how to do that, but this is really, really intriguing. And from my point of view, of course, I tend to be an optimist. Some people see this. I think Sujata sees this and says that's why you can't prove conjecture A. But I see this and say that's probably we're going to prove that mu equals 0 conjecture holds. We'll see. Okay. So let's look a little more closely at the finite layers in the cohomology. In particular, we look for cases where the cohomology is particularly simple. This is all of what I'm going to talk now is joint work with Devanjana Kundu. So we have an elliptic curve E over K. P is an odd term of good reduction. Let me set L to be the field obtained by joining points of order P. Then we know the Galois group of L over K is contained in GL2Z mod P. And if E doesn't have complex multiplication and P is generic, then this should be equality in general. In this case, there's a lot that we can say about the cohomology of this Galois group with coefficients in E bracket P, where G is a subgroup, where G is understood to be a subgroup of GL2Z mod P. So here's the little theorem. Suppose I have G like that and a normal subgroup Z with the following property, that P doesn't divide the order of Z and Z acts without fixed points in E bracket P. Then, in fact, you can show that the cohomology vanishes. Okay, that's not so hard to use. The point is that when you have finite groups involved and the orders are co-prime, the cohomology will vanish in positive dimensions. So from the definition of cohomology. And then since the H0 is fixed points, and I'm saying there is no fixed points, H0 is 0 as well. So the cohomology, this conditions may force the cohomology of Z to be 0 with coefficients in E bracket P. But then you have Hochschild-Scher spectral sequence, which allows you to relate the cohomology, which is this E2 term in the spectral sequence is HK of G mod Z, HL of Z. But we just said all of this cohomology is 0. So that means the E2 term vanishes. But the E2 term converges, the spectral sequence converges to the cohomology of HK plus L, and the E2 term is all 0. So that means this is all 0. So that shows you the cohomology of G is 0. Okay, an example of this is, for example, if E doesn't have complex multiplication and this Galois group is GL2Z mod P. In fact, this case was proved by Gross, and it was seeing his proof that I just abstracted it to the proposition I just showed you. So in that case, you take Z to be scalars. But here's another case that Devanjana and I observed. If I have G is the Galois group of this extension, suppose one of these conditions are satisfied. Either there are no points of order P over the base, or G contains SL2Z mod P. Then also the cohomology of G vanishes. Okay, why do we care about the cohomology of G vanishing? Because I can use it for descent. You see, if I set L to be K adjoint E bracket P, restriction is a map. It takes H1GK to H1GL, but not just any, it takes it in fact to the subgroup of H1GL, which is fixed by G. And in fact, there's a long exact sequence. This also, by the way, comes from a spectral sequence, but there's the map restriction here is bounded on both sides by cohomology of G, H1G here and H2G here. So in particular, if you know the cohomology of G is 0, this has to be an isomorphism. So if you're looking at GK E bracket P and you go up to a bigger field and you take the G invariance, you just get an isomorphism. Okay. So, but the point, why do I like this? Because remember, what is L? L is K adjoint E bracket P. That means GL acts trivially on E bracket P. And I just told you when you have trivial action, this is just a harm. So that means H1GL E bracket P is harm GL into E bracket P. So that means H1GK is G invariant harms. So now I have a simple description of H1GK, G invariant harms from GL into E bracket P. Equivalently, I can write this as a non-degenerate pairing from this thing cross GL into E bracket P. Namely, I take an element here, that gives me a harm, apply it to this element, I get an element of E bracket P. Okay. So now under this thing, if I take, and this is a non-degenerate pairing, so if I take a subgroup of this, I have a dual, which will be a quotient of this. So in particular, if I take H to be, excuse me, if I take H to be the elements, sorry, not a quotient, a subgroup. If I take S here to be a finite subgroup of this thing, then H will be the things which are orthogonal to S. It's an open subgroup of GL. And then it's an open subgroup, therefore I can look at its fixed field. It gives me an extension L sub S. And the Galois group here is GL mod H. And that identifies my S with a harm, not just from, like here I had harm, the big Galois group, but now I have a harm of a finite extension, namely this extension. So in particular, if I choose for my S, the Selmer group, I will get a particular extension. And similarly, I can look at the fine Selmer group. So what I get is I have K, I have L, which is K joint E bracket P. Then I get two extensions. One is L sub R, and then one is L sub S, just from this duality. So the Galois group of this whole thing, LS over L, is harm, is the dual of the Selmer, the P part of the Selmer group. And this piece here is the dual of the fine Selmer group. By the way, this raises the question, now this part is unramified because I told you the Selmer group catches the class group, but it raises the question, and how do I go from here to here? So that means there must be intermediate extensions where I get more and more of the ramification. So I have here now a new kind of question on elliptic curves that I can try to answer by imitating classical class field theory. So this is the question of natural intermediate extensions related to the growth of ramification. Okay, so now I'm running out of time. So let me say that as an application of the above duality, you get a certain control theorem. I'm using Mazur's terminology for control theorem, namely that under certain circumstances, the fine Selmer group downstairs is the G invariance of the fine Selmer group upstairs. So we need some hypothesis. This is something I proved with Devanjana. And there's a more sophisticated version that Meng, Fai, Lim, and Devanjana have just proved, a bigger control theorem. Okay, so I think maybe I'll skip this proof and go to say last thing that I want to say. Okay, so now this is the last thing maybe I want to say, that remember I told you there's this enigmatic thing. You have a certain field associated to the fine Selmer group, which is unramified, and you have a certain field associated to the whole Selmer group. And so and I said there must be a way of getting from one to the other as I increase the ramification. So it suggests that it might be possible to define higher fine Selmer groups, and we can actually do that. We call RPMJ. So these are groups. They sit in a family like this. It's a kind of filtration where you start off with the fine Selmer group and you end up with the Selmer group, and you have these things in between. Remember I told you this thing is imitating the class group? Well, now I want to say, I want to get from the class group back to the Selmer group. So I want to find things that sort of interpolate from the class group back to the Selmer group. So the way you do it is you weaken the local triviality conditions. You go back to the descent sequence and you weaken the local triviality condition where the jth one of the sequence, instead of being killed by p to the m, you say it's only killed by p to the j, and that gives you the sequence of groups. And now you form this diagram of fields using the duality that I explained using the cohomology, and you get now a two-dimensional family. So here is where we were getting the L is K joint E bracket P, then the next part of the Selmer group, and so on. And here I'm getting things in the filtration in the fine Selmer group. And And now we can ask what, you remember Iwasawa theory questions are about what happens in the limit. It's all like that I take the inverse limit of this thing, and then, or the direct limit of the fields, and then talk about the Galois group of the big extension. Iwasawa theory is all about that. But the point is now I have two dimensions. I have many different ways of getting to infinite extension. I can go straight up. I can go up these towers. In other words, fix the point in the filtration and go straight up. So now I have p squared, p cubed, and so on like that. So this is the fine Selmer tower. And way up here, if I take the endpoints of these things, I get the usual Selmer tower, but I have all these in between. Where does that lead us? I think what's going to happen is it's going to enable us to construct a whole bunch of new Galois modules, which will interpolate between the fine Selmer and the Selmer. And why that's interesting is, again, I repeat, because fine Selmer seems to be more intimately connected to classical Iwasawa theory and ideal class groups, and the full Selmer is connected to elliptic curves proper. And this thing is going to help us to go from one to the other. And so it could be quite intriguing if we can prove anything about that. What kind of Iwasawa theory does this lead to? I'll let you know when we figure it out more in the next talk. Thanks a lot.
Yeah, thank you so much, Professor Kumar. It was a wonderful lecture. So now it's open to the, hello, Ram.
Oh, hello, Kalyan. Congratulations on your directorship. Is it possible that I can ask a question or two?
Yes, sure. I'm just going to keep it open. So go ahead, Ram.
Okay, so two questions I have. One is with respect to this famous conjecture about the class numbers of the totally real subfields of p to the n cyclotomic field. There's a conjecture that the class number of q zeta p to the n plus 1, the totally real subfield of that, has class number 1.
Yeah.
And do you think that your work can shed some light on that conjecture?
So the class number of the real subfield, right?
Yeah.
Yeah.
I mean, there's the original conjecture started with 2 to the n.
Yeah.
But I think numerical calculations seem to show that for other primes too, the same thing works.
So I don't think the methods we used will work, because remember what we're doing in everything we were doing, the results I showed you is about the minus part of the class number. So it simply doesn't see the plus part. Whether there's some other variation of this method that will see that, I don't know. But as it stands now, this method sees only the minus part.
And
Somehow
the other thing,
that seems to be
that's yeah. So the other question is with respect to this nu in the Iwasawa theorem. You said nu was a constant, but is it? I mean, there's that co-kernel, finite kernel, and finite co-kernel in the structure theorem.
Right.
Won't that mess up the nu being? Can it not fluctuate with?
So I don't know anybody who actually studies the nu. Maybe that's why.
Looks like an interesting thing to study. I mean.
Yeah, because I mean, where does it come from? I mean, it just comes from writing down, if I have that kind of module, what is lambda mod lambda to the p to the n, or what is m mod n p to the n? So that's where it comes from. I don't know if anybody who studies the nu.
And one last question is, it looks to me like you can do this whole thing over a function field, over a finite field. And maybe function fields over a finite field. You can take a prime over the function field and develop Iwasawa theory over that, right?
Function fields over finite fields is where the subject started.
Okay.
In fact, Iwasawa was trying to do for number fields what was known in function fields. I mean, see, point is, you have to understand in function fields, especially after Wey's way of looking at the curve over bigger and bigger finite field extensions, that is the Jacobian is the class group. See, on a curve, the geometric version of the class group and function field version of the counter is the Jacobian. Divisors of degree 0 modular principal divisors is exactly the Jacobian. So from Way conjectures, you know how that grows. The number of points on the Jacobian, you know how it grows. You have a formula in terms of the roots of the L function, and you have growth in terms of estimates for those roots.
Yeah,
so Iwasawa, looking at that theory, was trying to say, what do we do in the number field case that could imitate that? That's why he took mass field. Yeah.
You're absolutely right that the original motivation for the Iwasawa thing was that example, that's the analog of the cyclotomic extensions in the functional field. But now that since the program has been enlarged, you're looking at elliptic curves, so is it possible now to go back to looking at elliptic curves over function fields or finite fields and do your fine Selmer group calculations in that context? That's what I was asking.
Yeah, no, it's interesting question. I'm not sure. I'm not sure where it will lead, but it's an interesting question. And I don't know if it's been looked at at all.
Yeah.
Thanks a lot, Ram. Is there any more quick questions? Because we have another talk lined up. So from the audience, is there any question from YouTube chat? People who are...
No, sir. No.
So is any question here? Okay, so we have this. Thanks a lot, Kumar, and it was nice.
Thank you.
We'll see you soon.
Nice to see you. Thank you. Thank you.
The situation normalizes, both of you will be coming here.
Yes,
I mean,
hope so.
it's like